let's take a look at energy sources. So of course humans have used lots of different types of energy sources as long as there have been humans around. And the types of energy sources that we have used has changed over time, right? Early in human history, we used lots of wood. We burned the wood. That was a great energy source. As time went by, people started to use more and more fossil fuels, and now we even have energy sources like nuclear energy and hydroelectric energy and wind energy. So it's a big topic, and one of the ways that we attack a big topic is to categorize things. And one of the ways that we can categorize energy sources is as primary sources and secondary sources. A primary energy source is a source which hasn't been transformed or converted. It's like an energy source in its initial form. So this would be things like fossil fuels, or if you cut down wood and use that to burn in a campfire, that's a primary energy source. A secondary source, on the other hand, that's a source of energy which comes from a transformation of the primary energy source into another energy form. So, for example, electrical energy that we get out of our electrical sockets, that is a secondary energy source because we can trace that energy back to another source. The electrical energy coming from the socket had to come from a power plant somewhere, maybe a coal power plant, and that coal power plant was burning coal. So the secondary energy source of electrical energy that's coming out of the sockets can be traced back to the primary energy source, which would be the coal that's being burned in the power plant. So these primary energy sources are like the original energy sources for the energy that's being used by humans. And we can categorize these primary energy sources that are used by humans into two other categories, into renewable and non-renewable. Renewable energy sources are sources which can be replenished or renewed or rejuvenated or regrown on human timescales, so on the order of decades or maybe even centuries. So renewable energy sources include things like wind, solar, biomass, which would include, say, cutting down a tree and burning it, or growing corn and soybeans and converting that to bioethanol, which can be then added to gasoline. Also hydroelectric is a renewable energy source, and geothermal energy, energy that's derived from the earth, is a renewable energy source. Non-renewable energy sources are sources where the source cannot be replaced after use in a meaningful amount of time. And the two most common non-renewable energy sources we think about are fossil fuels, which take millions and millions of years to form under not very common geologic processes, and uranium. Uranium can't be made in measurable amounts anywhere except in the centers of stars. So that source of nuclear energy is not a renewable energy source. If we look at the types of sources that are used by humans, it turns out that by far fossil fuels provide most of the energy used by humans. If we look at the data for 2019, and this comes from BP, British Petroleum, fossil fuels provided 84.5% of the energy used by humans. And fossil fuels can be broken down into three big categories. As a solid, fossil fuels are coal. As a liquid, fossil fuels are oil. And as a gas, fossil fuels are natural gas. And here are the percentages of those. Hydroelectric power provided 6.4%. Nuclear power provided 4.3%. And all other sources provided 5%. So those other sources include things like wind power and tidal power and other relatively minor sources. So as you can see, fossil fuels are by far the dominant primary source of energy for humans across the world. Now, each source of energy has different characteristics. So the way that you get energy out of coal, for instance, is a very different process than how you get energy out of, say, the wind or out of nuclear fuel. And we're going to talk about how we can get the energy from a source and make it into something usable by humans a little bit later. But another way to think about each energy source is how much energy you can get from that source. And we quantify this in two different numbers. One is with specific energy, and another way is with energy density. Specific energy is the energy released by a source per mass of that source. So it's energy released per mass. So the unit of this is the joule per kilogram. Sometimes it's stated in megajoules per kilogram, but it's the energy per mass. So if I have 1 kilogram of a source, it tells me how much energy I get, how many joules I can get per kilogram. Energy density is the energy released by a source per volume. So it is given in units of joules per cubic meter, or sometimes megajoules per cubic meter. So it's telling me how much energy is released for every cubic meter of volume of that source. So for example, coal. Coal has a specific energy ranging from 20 to 60 megajoules per kilogram. So for each kilogram of coal, I could get 20 to 60 megajoules for each kilogram. And the energy density of coal is somewhere between 20 million to 60 million megajoules per cubic meter. So for every cubic meter of coal, I can get 20 million to 60 million megajoules of energy. Uranium, on the other hand, has a specific energy of about 8 times 10 to the 7 megajoules per kilogram. So that's a very large specific energy. We can get a lot of joules of energy for each kilogram of uranium. The energy density of uranium is approximately 1.5 times 10 to the 15 megajoules per cubic meter, which is an enormous amount of energy to get per volume of uranium. Now, a common way of taking thermal energy from a primary energy source and converting it to electrical energy is by means of something called a thermal power station. So this is a general design for converting thermal energy into electrical energy. And the idea is that we have a primary energy source and we somehow cause it to release heat. And the heat is transferred to water inside of our thermal power station. And if we transfer heat to the water will eventually boil and convert to steam. And if it's high pressure steam, as it is in a thermal power station, the high pressure steam is then sent through a tube to a turbine. And a turbine is essentially a big propeller. And as the steam passes through this propeller, it causes the propeller to spin. And the steam, as it moves, the steam has lots of kinetic energy. And that kinetic energy is transferred to the propeller blades, and the propeller blades spin. And so now the propeller blades have kinetic energy, and they're connected to an electrical generator. And an electrical generator converts the kinetic energy of the propeller blades into electrical energy, which can then be sent into electrical wires and eventually to your home. After the steam has passed through the turbine, the steam now has less kinetic energy and less internal energy, so it has a lower temperature and it's not moving as quickly. And it passes back through something called a condenser, and the condenser will convert the steam back into liquid water, and the liquid water goes back into the boiler over here, where it can start the process all over again. The last thing we'll look at is something called a Sankey diagram, and there are many different types of Sankey diagrams, but we're going to use them to depict energy inputs and energy outputs in some kind of process. So a general drawing of a Sankey diagram might look like this, where we have energy inputs over here, and then we have all these arrows. And in these diagrams that we're going to draw, a straight arrow is going to represent the energy that comes out as useful energy. So that's the useful energy that's output from the process. And these other arrows that are bent are going to represent energy that's wasted in the process, energy that's lost. This is called degraded energy. So degraded energy is energy which is no longer useful. Another term would be it's wasted energy. So for example, if we looked at the energy input and output from a coal-fired power plant, the Sankey diagram for that would look like this. We have the energy that's input from the coal into the power plant, and then the energy that's output to the generator, so that's the useful energy output, is about 40% of the energy that's input. About 10% is degraded due to friction. So that's lost due to the rubbing together of the parts within the power plant. And another 50% is lost as heat. So that's just heat that leaves the system and never gets to be used. So you can see the degraded energy in a coal-fired power plant is approximately 60% of what was input, and the useful output to the generator is about 40% of what went into the power plant.